everyone, today we're going to be learning about the reaction called Robinson annulation. This is a reaction that's part of chapter 22, so let's first go over some basics. In previous chapters, we've always seen ketones and aldehydes acting as electrophiles, meaning a nucleophile will attack them at the carbonyl carbon, which keep in mind, carbonyl carbons have a partial positive charge, making them good electrophiles. In chapter 22, though, we are now seeing carbonyls acting as nucleophiles. The way we transform carbonyls into nucleophiles is by using a base to abstract an alpha hydrogen, which, remember, an alpha hydrogen is just a hydrogen that's one carbon away from a carbonyl carbon. This leaves behind a negative charge. Now the molecule is called an enolate ion. This negatively charged carbon is a good nucleophile, and it can be used to attack electrophiles. You'll see a lot of reactions in chapter 22 in which enolate ions act as nucleophiles and attack electrophiles. This video is going to go over probably one of the most complex reactions from chapter 22 called Robinson annulation. So Robinson annulation is a combination of three reactions. The first reaction being Michael addition, the second reaction being cyclic aldol condensation, and the third reaction being dehydration. Robinson annulation involves a reaction between cyclohexanone with an alpha-beta unsaturated carbonyl as well as a strong base. This product probably looks really complex to you, but it'll be easier if we explain the mechanism behind it. So Robinson annulation is going to happen in three steps. The first step being Michael addition. So the first thing that's going to happen with any chapter 22 reaction in general is we're going to have a base abstract our alpha hydrogen, leaving this carbon behind with a negative charge. This negatively charged carbon is a good nucleophile, which in Michael addition, nucleophiles are referred to as Michael donors, because they donate electrons towards our electrophiles, which are called Michael acceptors. Here, our electrophile is our alpha-beta unsaturated carbonyl, particularly this carbon at the end of the alpha-beta unsaturated carbonyl. The reason this is a good electrophile is because good electrophiles have partial positive charges. If we look up here at how this alpha-beta unsaturated carbonyl resonates, we can see that when the pi electrons resonate, this carbon becomes fully positive. Because of that, this carbon has a partial positive charge, and it's therefore a good electrophile. So what will happen in Michael addition is our lone pair of electrons from our nucleophile is going to come and form a bond with our electrophilic carbon of our electrophile. And now this carbon is going to then have too many bonds, so we're going to end up having to resonate the pi electrons. So these electrons are going to move here, these electrons are going to come onto oxygen, and we're left with this structure in which we've formed a new bond here that I've highlighted in yellow. So this negatively charged oxygen attached to a double bond here is called an enolate, which if we kept this negative charge on oxygen where it is, and use this negative charge, this lone pair, to protonate oxygen to alcohol, it'd be called an enol. What we want to keep in mind, though, is that the keto form, so this molecule where this oxygen is in the form of a ketone group, the keto form is most stable. So a process is going to happen called keto-enol tautomerization. Keto-enol tautomerization is basically a process in which our enolate resonates to the keto form. So these electrons and oxygen are going to come down, pushing these electrons onto carbon. And now we've reformed our ketone. So to neutralize this negative charge on oxygen, this negative charge is going to pick up a hydrogen from water that's roaming around in solution, and it's going to be neutralized. So now we see that the product of Michael addition is always a diketone, in which we've joined our Michael donor and our Michael acceptor, formed a new bond, and the double bond on the alpha-beta unsaturated carbonyl is now gone. So our product from Michael addition, our diketone, can now go on to react in our second reaction, which is cyclic aldol condensation. Let's first go over what aldol condensation in general is, though. So we want to keep in mind that the first thing that we have to do with any reaction in this chapter is add a base in order to abstract an alpha hydrogen. So here we can see we have a negatively charged carbon. This came from abstracting our alpha hydrogen. This is now called our enolate ion. Aldol condensation is basically when our negatively charged alpha carbon nucleophilically attacks another carbonyl carbon from another molecule in solution. So it's going to nucleophilically attack this carbon, pushing the pi electrons between carbon and oxygen up, and we end up having formed a new bond. This negatively charged oxygen is then going to grab a hydrogen from water, and we can see that in our product, this is called an aldol. We've formed a new bond, and the carbonyl that was attacked now turns into an alcohol. So let's see how this relates to cyclic aldol condensation. So since we still have base present in solution from our first step of the reaction, the first step that's going to happen here is we're going to use this base to deprotonate an alpha hydrogen from one of these carbonyls. But the problem I see here, though, is that we have 4 possibilities of alpha hydrogens to deprotonate. So now I want to look at our molecule in general. I see that this is a diketone, so we have 2 carbonyls. Since cyclic aldol condensation involves a reaction between 2 carbonyls, I'm going to look to see if I can do an intramolecular reaction, which is basically when the molecule reacts with itself instead of swimming around in solution and trying to find another molecule to react with. If I can do an intramolecular reaction and form a stable product that way, that would actually be favorable so that the molecule doesn't have to go around and look for another carbonyl to react with. So I'm looking here, and it turns out that if I deprotonate this alpha hydrogen on this side of the carbonyl, we actually can use this negative charge to form a stable 6-membered ring. So this negative charge can be used to nucleophilically attack the carbonyl on our cyclohexane ring, and these electrons are going to come up. When we look in our product, we've actually formed a 6-membered ring, and this is cyclic aldol condensation. So we did the exact same thing as we did with regular aldol condensation, except we just did it in order to form a ring. So now this negatively charged oxygen can pick up a hydrogen from water, forming our product here, which is where we formed a ring. This new bond that was used to form a ring, I highlighted in green. So our final reaction of Robinson annulation is dehydration. So this is basically when we get rid of this alcohol here and we end up forming a double bond here. So in order to do that, we're going to first need to deprotonate an alpha hydrogen that is closest to the alcohol, since these electrons are going to be used to come down and form a double bond, kicking alcohol off. But we need to keep in mind that alcohol on its own is not a good leaving group. So to turn it into a good leaving group, we're going to use a lone pair on oxygen to deprotonate a hydrogen from water. So this is going to turn alcohol into H2O+, which is a good leaving group. So the electrons that were left over from the alpha hydrogen are going to come down and form a double bond, kicking off water. So now we have our final product in which we've kicked off alcohol and formed a double bond here. So I've written for you guys a steps condensed page, basically showing not everything in the mechanism, but just the spots where we deprotonated and used those electrons to form new bonds. So just keep in mind that with Robinson, you start with cyclohexanone, you're reacting with base and an alpha-beta unsaturated carbonyl, and you start with Michael addition, and then you do cyclic aldol condensation, and then dehydration. So that pretty much concludes our video here. Please let us know if you have any questions. We'd be happy to help you. Have a good day, guys.